Okay, dear students, can you see now? Hello?
Yes, ma'am. Yes, ma'am.
You can hear, you can see the slides.
Yes, ma'am.
Okay, can I start the lecture of today?
हाँ जी, ma'am.
Okay. So, dear students, today we'll be talking about ozone depletion. Right? This is also the part of your syllabus. As you all know, ozone is a gas composed of three atoms of oxygen. It is bluish gas that is harmful to breathe. Nearly 90% of the Earth's ozone is in the stratosphere and is referred to as the ozone layer. Now, ozone absorbs band of ultraviolet radiation called UVB. And this is the structure of ozone. You can see the resonating structures of ozone. You are well aware of this structure. And these are the layers of ozone, right? So these are the different atmospheric layers, and generally the ozone is present in stratosphere, which is very helpful to the human beings and the vegetation, the animal kingdom, and all. Right. So let us come to the scientific background of this ozone. Ozone was discovered by Schonben when observing electrical discharges. Ozone shown to be natural atmospheric constituent. Right? So experiments show that ozone strongly absorbs solar ultraviolet radiations. Proof that the most of the atmosphere's ozone is located in stratosphere was found in 1930. And in 1920, Dobson, an Oxford scientist, perfected an instrument to monitor qualitatively total atmospheric ozone. And after the name of this scientist, the unit is named for ozone, that is Dobson unit. It is generally measured in Dobson units. Now, if we see the current signs of ozone depletion, it is observed that in Antarctica, the Arctic, and the mid altitude is still continuing due to past emissions of CFCs, and it will peak in the next few years. The Montreal Protocol is working, and ozone depletion from the protocol's controlled substances is expected to start recovering within the next decade or so. Even with full compliance of Montreal Protocol, the ozone layer will remain particularly vulnerable for the next decade or so. Failure to comply with the Montreal Protocol will delay or even prevent the recovery of ozone layer. And as you all know, dear students, World Ozone Day is celebrated on 16th September. In 1994, the United Nations General Assembly proclaimed 16 September the International Day for the preservation of the ozone layer. It is just to commemorate the date of signing, that is in 1987, of the Montreal Protocol on the substances that deplete the ozone layer, and the resolution is 49 by 114. So every 16th September every year it is celebrated as World's Ozone Day. And as I told you, the ozone, it is measured in Dobson units, is after the name of the scientist Dobson. The Dobson units indicate how much of the given trace gas there is in the air above a certain point on Earth. A proper unit in the international system of units would be thus kilogram per square meter. So this is the SI unit, kilogram per square meter. And imagine if 100 du of ozone were brought to the Earth's surface, it would form a layer 1 millimeter thick. In the tropics, ozone levels are typically between 250 to 300 du year around. In temperate regions, seasonal variations can produce large swings in ozone levels. For instance, recorded ozone levels are found as high as 475 du and as low as 300 du. So, this is how we see the ozone measurement. Now, what types of ozone are present? Generally, ozone can be split into two major types. One is the stratospheric ozone and another is ground level ozone. Stratospheric ozone is generally called the good one. Good, why? Because it protects living things from ultraviolet radiations from the sun. And ground level ozone, as we know, this is bad ozone. Why it is named as bad? Because it can trigger a variety of health problems, particularly for children, the elderly, and the people of all ages who have lung diseases such as asthma. Now, where these ozones are present? As the name suggests, the stratospheric ozone, this is present in the stratosphere. Stratospheric ozone, also known as the ozone layer. So, this is just named as the ozone layer and forms high in the atmosphere 6 to 30 miles above the Earth's surface. When intense sunlight causes oxygen molecules to break up and reform as oxygen ozone molecules. So in this way, ozone forms is formed from oxygen. So these ozone molecules form the ozone layer and are commonly referred to as good ozone. So in the stratosphere, the ozone present is called the good ozone. At concentrations as high as 12,000 ppb, the EPA considers anything over 70 ppb to be unhealthy for human health and welfare. So, at concentration as high as 12,000 ppb, this ozone protects and shields people, trees, crop property, and microorganisms from the harmful effects of the sun's ultraviolet light. Now, you will ask me, what is EPA? EPA is United States Environmental Protection Agency. So generally there are different agencies working on the measurements. Right. So this was about the good ozone. Now let us come to ground level ozone, which is referred to as bad ozone. Ground level ozone forms just above the Earth's surface, up to about 2 miles above the ground, and impacts human, animal, and plant respiration. Although ground level ozone is less concentrated than the stratospheric ozone, its impacts on human health and welfare make ground level ozone bad ozone. Right? So, the ground level ozone is an irritant and can negatively affect human health and welfare. The weather plays a substantial role in the formation of ground level ozone. Ground level ozone concentration typically are highest on days when it is warm. Hot days also the level is more. with low humidity when the wind is light or stagnant. So, this is about the good and the bad ozone. Now, let us see, where is ozone found in the atmosphere? I've told you the highest content of ozone occurs in the layer that is from 15 to 50 kilometer. This is the maximum concentration of ozone which is found, and the peak is here, right? So in the stratosphere it's maximum here, right? So note higher concentration in stratosphere compared with the troposphere. Now if we see the troposphere, the concentration is, this is the ozone density and this is the altitude. Now in troposphere it is very less, it increases. Can you see it properly? Right? So in troposphere then like this, and then it vanishes. So tropospheric ozone is harmful, stratospheric ozone is beneficial, as I told you just now. So these are the layers, and this is the ozone layer. Can you see it? That is from 15 to 50 kilometers. This is the maximum concentration of ozone. In ground level, the ozone is very less. So these are the different zones where the different activities are there, right? So in ultraviolet rays, we see that there are three regions: UVC, UVB, and UVA. You should observe that in your sunscreens also you have written that it is protecting your skin from the different A, B, and C, right? So this also you should see on the sunscreens which you buy for your own self. So this is the earth, right? And on the earth there are the different activities which are going on. There is fire extinguisher, there are different chemicals, there are different industries, and there are different aerosols, and there are different activities which are releasing the um, different components which are now giving us the ozone, right? So leads to the formation of ozone, right? So if we see, this is the protective layer, this is the protective layer, right? And this is the stratosphere where the ozone is present, and this is the troposphere, just 6 miles. So there are too much cars, trucks, power plants, and factories all emit air pollution that forms ground level ozone, which is bad. Now, too little here in this. Many popular consumer products like air conditioners and refrigerators involve CFCs or halons during their either manufacturing or during their use. They are released. Over time, these chemicals damage the Earth's protective ozone layer. So this is becoming thin, and hence leading to the vulnerable situation which is happening on the earth. Now these are the three scientists who have received the Nobel Prize in 1995 for their work in atmospheric chemistry, particularly concerning the formation and decomposition of ozone. So it was first observed by these three scientists, one from Netherlands, Cousin, from USA, Molina, USA, Rowland. So in 1995, they got the Nobel Prize for this work. Let us come to one more terminology, that is ozone depletion potential. So these are the just small 2 marks questions also which are being asked. What do you understand by ODP? Ozone depletion potential. The ODP of a compound is defined as the ratio of the total amount of the ozone destroyed by that compound to the amount of the ozone destroyed by same mass of CFC11. Now you will ask me why I have taken this CFC11, why this CFC11 is adopted for the calculations of the ratio. The ODP of CFC11 is defined to be unity. Why this is taken? It is also referred to as CFC11 or R11. Now the question arises why this has been selected. Because it has the maximum potential amongst chlorocarbons because of the presence of three chlorine atoms in the molecule. And chlorine is the biggest culprit in causing the ozone depletion. We'll come across this also, right? So reduction of ozone concentration in the stratosphere, that is known as ozone depletion. This is good ozone which filters out the UVB radiation. Additional UV can cause negative effects on human crops and the built environment. Occurs when ozone depleting substances catalyze ozone destroying reactions and was first noticed by the scientists in 1970s. So in 1970s they were first observed. These are the different classes of ozone depleting substances. We have halones. Generally they are haloalkanes. Very high, severity is very high. Main use, fire suppression, these are used. Some examples are halon 1301, halon 1211. And then there are CFCs. You all know about freons. Severity is high. They are used in refrigerations, AC, aerosols, and the solvents. And generally the examples are HCFC 140, HCFC 22. So due to the decrease in the emission of these, N2O, laughing gas, is becoming important nowadays and will likely to be largest contributor to this ozone depletion, right, in 21st century, as reported by Ravi Shankara in his paper in 2009. Causes ozone loss through different mechanism. So N2O, it will also cause ozone depletion by different mechanism. The main anthropogenic emissions from agriculture and fuel combustion, not even classified as ODP, is most impact methodology. So this will be the most affecting now. And we have done all this in oxides of nitrogen. Now these are the different ultraviolet spectrum. You see that we have the different, this is the UV radiation range, that is from generally 300 to 200. 300 to 200, we will see that we have UVB and UVC. So generally we have the range from 400 to 100, right? So the UV spectrum, if we observe, it has got four regions. One is the far UV 100 to 200. Can you see this clearly here? Right? This is the far UV. Then you have the UVC, right? 200 to 280 nm, right? And then you have UCB, that is from 280 to 315. Then you have UVA, that is 315 to 400. This is also very important, and you should always note that these are mentioned on your sunscreens, as I told you. So these are the different UVA, B and C, right? UVA not absorbed on Earth's atmosphere, UVB partially absorbed by the Earth's atmosphere, UVC completely absorbed by the Earth's atmosphere. Now, ultraviolet radiation, generally 230 to 830 nm, damages nucleic acids, right? So nucleic acids, your DNA and all, they are disrupted, then stops reproduction of the cells by breaking apart the DNA bonds. Ozone production peaks at 185 nm. So this is the ultraviolet radiation spectrum, which is showing that the peak is at what? 185 nm, right? So this is the peak. And ozone absorbance and destruction between 200 to 320 nm, right? Now let us come to depletion of ozone. This was all the background. Now let us come to the depletion of ozone, how it occurs when ultraviolet light, right, from the sun in this range 175 to 220 nm strikes the Earth's atmosphere. It causes photolysis of O2 molecules. Right, now these O2 molecules, they are converted into reactive oxygen atoms. The reactive oxygen atoms, now what happens? They combine with oxygen to form ozone. So in this way, ozone is formed. Right. O3 formed is distributed in the stratosphere. As I told you in the figure also how it is distributed in the stratosphere. I gave you the range also, and even diagrammatically I had shown you how it is distributed, right? Forming a layer which is thin in some places and thick in others. What is the function of this? O3 absorbs harmful ultraviolet radiations, and ozone generally absorbs this ultraviolet radiations and form O2 and O. Right? So the cycle is again repeated. In this way, we have an equilibrium between them. Thus, we are safe and protected from the harmful effects of ultraviolet radiations. Although, as I told you, this is the 3. That is, 3 is O3 plus H nu gives this. This is the reaction 3. Although the 3 reaction destroys O3, but it also produces reactive oxygen atoms which combine with O2 to produce more O3 to compensate the loss. So again, if I come to this slide, this is the ozone, it is forming this will again react with what? Oxygen and form O3. So the cycle is what? The cycle is repeated, right? So this results in an equilibrium concentration of O3. However, this equilibrium is disturbed when reactive chlorine atoms released from photolysis of chlorofluorocarbons wafted into the atmosphere. As soon as they are released in the atmosphere, the culprit is chlorine atoms, right? So they will what? These atoms create an imbalance by destroying the O3 molecules. The loss of O3 molecules in the upper atmosphere, right, is known as depletion of ozone. So this is actually what depletion of ozone is known. We all know depletion of ozone. These are the different ozone depleting compounds, freons. They were invented in 1930s, and the most common freon 11, freon 12, freon 113, freon 114. These are the common examples of freon CFCs. Chlorine released can strip off an atom to the ozone molecule, giving rise to ClO, chlorine monoxide, and normal oxygen is formed. Each molecule of CFC destroys thousand and thousand of ozone molecules. So this is how it happens, the halogen catalysis of ozone destruction. So this is just CFCs, right? Ultraviolet radiations, and we have the disruption going on like this. Right. So these are the ozone depleting substances. I told you just now, CFCs, HCFs, halogens, methyl bromide, carbon tetrachloride, and methyl chloroform. Now, mechanism of ozone depletion. The reactive chlorine atom. As I told you, this is the main cause of the depletion, these chlorine atoms, right? They initiate the mechanism of O3 depletion. Although CFCs are stable in the lower atmosphere, but when they reach stratosphere, the solar radiations splits them in reactive chlorine atoms. In this way, the CF2Cl2 this splits into the reactive chlorine atom, right? And this is followed as the chain reactions. The reactive chlorine react with ozone, we have chlorine monoxide, then the chlorine monoxide and this, they all both can react with some metal, right, species, and this can form to the formation of chlorine monoxide, right, a dimer. Then this, in the presence of ultraviolet radiation, again releases the reactive chlorine atoms and form ClOO. Now this can react and again lead to the formation of reactive chlorine atom. Chlorine atom can react with ozone and deplete this and form the normal oxygen and chlorine monoxide. So the net reaction, if we see that ozone, when ultraviolet radiation falls on them, we have a formation of three oxygen molecules. So this is the mechanism of depletion. Reactive chlorine plays the important role. Almost entire depletion occurs through the mechanism initiated by reactive chlorine atoms. Other mechanisms, though theoretically feasible, but have been ruled out. Right? So mechanism of O3 depletion. The species M represents another molecule that is unchanged in the reaction. So as a result of this mechanism, O3 hole is formed mainly over Antarctica. And that too during springtime in September and October. Scanty depletion also occurs over Arctic and few pockets of non-polar regions too. It's not that in Arctic there is no ozone depletion, but it is a lesser intensity. Arctic zone, unlike the Antarctica, where it is very cold every winter, the winter in Arctic stratosphere is highly variable. NASA satellite and airborne observations show that significant Arctic ozone losses occur only following very cold winters. जब बहुत ज़्यादा ठंड होती है तो आर्टिक में भी डिप्लीशन ज़्यादा होता है. So this is the view of the Antarctic ozone, right? So we only see these and ice, right? So in this way, we see that the ozone hole is defined as the area having less than 220 Dobson units of ozone in the overhead column between the ground and space. So this is the diagram which is showing the depletion of the ozone layer, right? And the Antarctic, and this is the figure taken from NASA. This is the chemistry behind it. Now, ozone hole has been mainly observed in stratosphere over Antarctica. Why? The depletion occurs mainly over Antarctica. It is a very common question, even asked in the examinations. In another part of stratosphere, two key reactions bind chlorine monoxide and Cl atoms. As I told you in the previous slides, chlorine monoxide is formed and we have the oxygen. So what happens? These ClO, chlorine monoxide, this is binded by NO2 and we have chlorine nitrate, ClONO2, right? It comes to be nitrate. So the reactive chlorine reacts with methane and we have HCl. So in this way, in the presence of oxides of nitrogen, this reacts with chlorine monoxide, right, and methane to form the Cl atoms. The chlorine nitrate, this, the chlorine nitrate and the HCl act as natural reservoir for reactive chlorine species. So they are bound now, they are not released, so there is no problem. But once these are tied up, the chain mechanism leading to ozone depletion is not initiated. So hence, in this way, these reactive chlorine monoxide and reactive chlorine atoms, they are bound and the reaction stops here. Hence, no O3 hole is created. But the problem is in Antarctica, conditions are different. During winter, two special types of clouds are formed. These are known as polar stratospheric clouds. On the vortex, it is very cold, right? Uh, it is very cold and the temperature is minus 90, which contains solidified nitric acid, that is trihydrate. HNO3 is present as trihydrate, which contains mostly ice. These clouds play important role in the depletion of ozone. Now, because the temperature is very low, it is very cold, these clouds provide surface on which chlorine nitrate formed undergoes two important transformations over the Antarctica. Now, the ClONO2, the chlorine nitrate which was formed, reacts with water and form HOCl, hypochlorous acid, right? And chlorine nitrate and HCl, they react to give us chlorine, right? So in this way, what we see that we have HOCl formed and we have chlorine. अब ये दोनों बन गए हैं. They will initiate the formation of reactive chlorine atoms. This converts an important reservoir of Cl atoms into hypochlorous acid and chlorine. Even under mild conditions, HOCl and Cl2 can be converted into active chlorine atoms, thus paving way for O3 depletion. In this way, the depletion occurs. These reactions also convert oxides of nitrogen known as scavenge Cl monoxide into HNO3. So these clouds on one hand reactivate chlorine atom sink and on the other hand remove scavenger chlorine monoxide. In this way, scavengers को भी हटा दिया और initiate कर दिया. And this picture shows the stratospheric clouds, right? So on July 25, 2016, researchers at Argentina's San Martin base spotted a bank of fantastically colored clouds floating in the stratosphere above the Antarctic Peninsula. So it was a beautiful scene captured by them, and this is the biggest stratospheric cloud. Now, during the sun, now the question is why it occurs at springtime. During this springtime, sun begins to shine over Antarctica skies. The hypochlorous acid HOCl right? And chlorine formed are photolyzed by the ultraviolet rays by sunlight to produce reactive chlorine atoms. So in this way, again now your chlorine atoms are formed and they will cause the ozone depletion. So this is in short the ozone depletions, the CFCs are released, right? And the CFCs rise into the ozone layer. Then what we see is the ultraviolet release chlorine from the CFCs. Now chlorine atoms, reactive chlorine atoms are released. The Cl now, this destroys the ozone. The ozone layer in the stratosphere is destroyed. Now what happens? Depleted ozone. We will see now here there are less ultraviolet radiations. Here the ultraviolet radiations are more. The intensity is more. And if there are more ultraviolet radiations, there will be skin cancer and many other health issues. So this is the process and effects of ozone depletion. As I told you, the CFCs, then they rise. So the male culprits now, as I told you, these are the halogens, fluorine or bromine. They detach when they rise up in the atmosphere, ozone depleted based on the substances reactivity, and they have a certain lifetime. They remain in that layer for a long time. Reduced ozone allows increased UVB penetration. And the end point is effects of increased UV, skin cancer, cataract, damage to crops, materials, and marine life. What are the consequences of ozone depletion? The human health uh, problems, skins, eyes, they are affected, crop yields, they are affected, more than two-thirds crops are damaged, phytoplankton, tiny plants near the surface of the sea are damaged, right? And the skin cancer, melena and non-melanin, they are destroyed. Premature aging of the skin occurs, and other skin problems also arise. Cataract and other eye damages also occur. There is a immune system suppression. How we can control? Two sets of compounds have been prepared to substitute CFCs. We can have hydrochlorofluorocarbons, right? And then we have hydrofluorocarbons, also called as alternative fluorocarbons, AFCs. So instead of CFCs, we can use these, and these are the different references. And thank you very much. Save the environment, save ozone. Less activity should be done to save the ozone layer. So I think so, dear students, you all have understood about the ozone depletion. So this is all for the day.
एक्सक्यूज मी मैम।
Yes.
मैम यूनिवर्सिटी साइट पे तो बस रीईयर की बोल रखा है कि रीअपियर्स वालों के एग्जाम होंगे।
कौन से उनके होंगे?
जो रीअपियर्स वाले बच्चे हैं मैम उनके।
अरे साथ में तुम्हारे हो गए, तब क्या करोगे?
नहीं मैम, वैसे पूछ रहे हैं हम।
हाँ भाई, देखो अभी तक कुछ आई नहीं है, बट तुम्हारे एग्जाम्स होंगे, लिखा हुआ है उसमें रीअपियर। बाकी आज मैं फिर से देखूंगी अच्छे से, पूरा मैंने मंगाया है, ठीक है, इसीलिए मैंने कल पोस्ट नहीं किया, बट मोस्ट लाइकली यू विल हैव द एग्जाम्स, राइट?
ओके मैम।
हाँ, बाकी मैं क्लियर आज सब कुछ पढ़ के अच्छे से वो लेटर मंगा लिया है मैंने, उस लेटर को अच्छे से पढ़ूंगी वो क्या कहता है, और फिर मैं आपके उस पर पोस्ट कर दूंगी। All important informations will be posted to you on your WhatsApp group. So please see the
तो वो देख लो, मुझे भाई अब वो तो यूएसए